We're now ready to talk about the second part of this section, 2.5. We're ready to talk about planes in three-dimensional space. And we specifically want to come up with a way of writing equations. Now, we know how to write equations of planes that are parallel to the coordinate axes planes. So something parallel to the xz plane, which comes out this way, would be y equal a constant, and something parallel to the yz plane, which would be like the screen, if this is z and this is y and this is x, something parallel to the yz plane would be x equal a constant. We know that, but what if I want the plane that goes this way, right? So how do I write the equation of that plane? Well, the first thing to realize is that if you're given any 3 points that are not on the same line, so between any 2 points, we know we have a line, but if the 3 points don't all lie on the same line, then there has to be a unique plane that lies through all 3 points. So 2 points connect with a line, but that third one is not on that line. Then the plane that connects the 3 points is unique. So just as a line is determined by 2 points, a plane is determined by 3 points that are not collinear. Given 2 distinct intersecting lines, so this would be not skew lines, which we talked about previously, but this would be lines that touch. There is exactly one plane, one unique plane that contains both lines. I like to think of this as maybe the spinner on a game. So you know how you thump the spinner, it goes around and selects a number. If the spinner is like a line, and if you have 2 of lines and they're both spinning like this, but they're touching at a point, that point is where they connect. So it's almost like the hands on an analog clock. As they spin around the clock, they're tracing out a plane, which is actually the face of that analog clock. Now, a plane can also be determined by a single line and a point that's not on the line. Why? Well, because if you have a line, you have 2 points, and a point that's not on that line gives you a third point, which gets us back to point 1. So a plane is also determined by a line and a point not on the plane. Now, we're going to come up with a different way of representing a plane, which is basically to take a point in space and to take a normal vector and say that the set of all points such that the vector from point P to Q is orthogonal in 3-dimensional space, that would be perpendicular to this vector n, forms a plane. Now, what does that mean? Take a point in space and say that if I draw from point P to all these points Q, all of those lines are perpendicular to n. So basically, what we're saying is that the normal vector to the plane and a point in the plane is enough to uniquely define the plane. So again, a plane is more or less like a flat sheet of paper. So if I'm taking, let's see if I can get this to stay still, a flat sheet of paper, and I have a vector like this, so it's coming off. You can see my pen here. Maybe if I hold it higher, you can see better. The pen is normal to the plane. If I take a point in the plane and that normal vector, I can uniquely define my plane. So that's what we're trying to do in this particular part of this section. Now, how do we do this? There are various ways of representing it, but one of them, of course, is the vector equation of a plane, which just says that this normal vector dotted with any vector connecting point P to Q that lies in the plane, the dot product has to be 0. Why? Well, the dot product, again, remember you've got magnitude of U, magnitude of V, cosine of the angle. Dot product has cosine, and the cross product has sine. How can you remember that? Well, let's see, dot has an O in it and cosine has an O in it. So dot product has the cosine, cross product has sine. So when we're looking at this right here, how do we know that it would come up to be 0? Well, the cosine of 90 degrees or pi over 2 is 0. So any vector that lies inside the plane inside this flat sheet of paper. So a vector that lies in this flat sheet of paper would be anything like this that's connecting anything, right? So it's like a line, a pencil on that flat sheet of paper. And those would all have to be orthogonal to the normal vector. So this is what we call the vector equation of the plane. This isn't actually the one that's the most useful for us. This is not the one we use the most often because we may not know a P and Q in the plane, and we may know the normal vector, but maybe we don't. We need to find it. So this is the scalar equation of a plane, and this is the one that we use the most often. This has a point that is in the plane, so we have to know at least one point that lies within that flat sheet of paper. And we need a normal vector, ABC. So if we have a normal vector, ABC, like this, and we have a point in the plane, then we can write what's called the scalar equation of the plane, which is the first component of the normal vector multiplied by the variable x minus the x coordinate of the point in the plane, plus the second coordinate of the normal vector times the variable y minus the y coordinate in the plane. So let me give you an example of what this would look like right down here. So let's say that we had a point 1, -2, 3. This is my point P. And I have a normal vector of 3, 0, 1, right? Then how would I write the scalar equation of the plane? I can't do the vector equation because I don't have another point in the plane, but I can do the scalar one. So I'm going to have 3 times x minus 1 plus 0 times y minus a -2 plus 1 times z minus 3 equal to the constant 0. And it's always equal to 0. And this will give me the scalar equation of that particular plane. Now, the general form would be if you multiplied everything out and had 0 on the other side. But if you do that, you're going to get a lot of different terms. Only 3 of the terms will have the variable in it, x, y, or z, and we can lump everything else together and call it d, if you will, where d is -ax naught minus by naught minus c z naught. In other words, that would include our -3, that would go to 0, and a -3 here, and that would become our d. So if we look at that, and we're trying to visualize what this looks like, then D actually turns out to be the opposite of the dot product of the normal vector with the standard position vector of point P. So this gives us this representation of all the constants in the scalar equation combined together into one particular point. So let's go ahead and take an example and see how we can write the equation of a plane. In this case, we're going to start in example 7 with a plane that contains 3 points which are not collinear. They're not on the same line. Right? So the first thing we need to do is we need a point on the line. I've got 3, which is overkill. No big deal. I need a normal vector. Okay, in order to write the scalar equation or the vector equation, I got to have a normal vector. Well, I have 3 points that I know are in the plane. All right, so I know they're sitting on this flat surface. I can get vectors by connecting any 2 of the points together. So I'm going to have to reuse one of the points. So there are lots of ways of doing it. I could do P to Q or Q to P, and then P to R or R to P, or I could do Q to R or R to Q. There are lots of different vectors, basically 6, that I could use to come up with 2 vectors in the plane. Now, why do I want 2 vectors in the plane? Because how do I know to get an orthogonal vector? If I have 2 vectors that are in the plane, to get an orthogonal vector, I take their cross product, and that will give me a normal vector. So in this case, there are lots of choices, but what I chose to do was P, Q, and PR. So I took the points, and I took the coordinates of P and subtracted from the coordinates of Q to get a vector in the direction of P to Q. And then I computed PR in the same fashion. And this gave me 2 vectors which are lying in that flat plane. Now to get a normal vector, and I don't know whether it's going to be the one pointing up or the one pointing down, but in either case, it's going to be orthogonal to the plane. It doesn't matter which one it is. I'm going to find the cross product of PQ and PR, which will be normal to the plane. Now this time I did have a 0 in here, of course, which will make the expanding by a row or column an easier method. So when we have IJK present, we always expand by that row. So when I cross out row 1 and column 1, I get the 2 by 2, -1, 0, -1, -1. I find the 2 by 2 determinant, and I get 1I hat. And then I cross out row 1 and column 2, and I get -1, 0, -3, -1. J hat is in the 1, 2 position. 1 plus 2 is 3, which is odd, so it has to be negative. And that gives me -1 J hat, and so on. And so I come up with this vector, which has to be orthogonal to the two that are lying in the plane. So now I have a normal vector. And again, if I had done the dot product in the other direction, if I had reversed the order, I would have gotten the same numbers, but with opposite signs. So another normal vector is -I plus J plus 2K hat. So that's also normal. One's going to point in one direction, one's going to point in the other. Take any of the points you want, P, Q, or R, doesn't matter. Substitute them into the scalar equation of the plane with the coefficients of the binomial parts being the components of your normal vector. And then you can multiply it out and you get this. If you had used a different point, when you multiply it out to get the general form, you're going to get exactly the same equation. And the combination of all those constants in this case gives us -7, which is that D, which is the opposite of n dot V, where V is the position vector of the point that we used. So when we're looking at this, you can see right here that we do have 3 points. This is our P, Q, and R, and they're lying in the plane. And I tried to turn it on edge so you could see they're lying in the plane. And then this is the normal vector, which the one we computed actually points down. And it is orthogonal to the surface of the plane, or normal to it. When we talk about a line in a plane, we generally will use the term normal. So let's take a look at this on CalcPlot 3D so you can see what it looks like. And I went ahead and labeled the different points. So first off, P, Q, and R are points. So those are down here. So I made them yellow and I made them larger, size 8. And then I labeled them by clicking in the select, and I selected a text label. And then when I did a text label, you'll see that it gives you where do you want to put the point. And this says at the upper right of that point. So it's not sitting right on top of the yellow ball. So it's upper right. So this gives me the labels that we have. And then I did the vectors that we computed. I think we did PQ and PR. So we have the vectors PQ and PR. But remember that PQ and PR are going to give you the vector in standard position starting at the origin. So there is a way in CalcPlot 3D that you can take that position vector and tell it to start at point P, right? So it'll go from P over to either Q or R. And I did that for both of these vectors. And then once I did that, oh, they're down here, these vectors down here. Make sure I've got the right ones. So I've got these vectors. And then the next thing that I did was I plotted the normal vector. Now, the one that we computed in our equation is actually the one on the opposite side. You can see it's right there. It's pointing out that direction. But you could have gotten the one with opposite, which would point in the opposite direction. Can you see that you can see the yellow balls on both sides of this plane? When you can see the yellow balls on both sides, then you know that that yellow ball is in the plane. Otherwise, it wouldn't show up on the other side, right? And so you can see your points P, Q, and R, again, on both sides, indicating that they are, in fact, in the plane. And then if I can get it to rotate, this is going to be tricky. I'm trying to get it dead edge on. I can't quite do it, but you can see right here now that P, Q, and R are sort of lining up along this darker edge, and the vector, normal vector is normal to the surface. Let's take a look at example 8. In example 8, we're instead given symmetric equations to two lines. We know that if we have two lines, now these are the two lines that we used before in example 6, so we know that these two lines are not skew. They intersect at a single point, 1, -1, 1. So we have a point where they intersect. Now think of these as sort of the hands of a clock, and as they, or spinners on a spinning board where you've got two spinners at the same time. And as they spin around, they create this plane, which would be the surface of the clock. So this will give us this point that they have in common will be a point in the plane. Now we also have direction vectors for the two lines, and these are given right here. We also know that the lines contain the points. The first one is the origin, the second one is 3, 0, 2. So we can find a normal vector by finding the cross product of the two direction vectors. The lines lie within the plane. So if we cross their direction vectors, we should get something that's normal to the plane. So in this case, I did expansion by the first row again, which gives us a normal vector, and you can see this one here. In this case, I was able to get it dead on in GeoGebra, and you can see P, Q, and R over here. P is at the origin, and then you have R and Q, and you can see that the normal vector that we find is in fact normal to the surface or orthogonal perpendicular, right? And if you want to see what it looks like in CalcPlot 3D, you can click here on the link. In the next part, we want to talk about how do you find the distance between a point and a plane. Now, we talked earlier about how to find the distance between a point and a line, which basically was to find the area of a parallelogram and then divide by the length of one of the sides to get us the perpendicular distance between the point and the line. But in this case, we don't have a line, we have a plane. So we have a point that's not on the plane and the plane, and we want to find the distance between the two. So again, if we're looking at this and we have this point, which is my fist, and we have this plane down here, you know that the shortest distance is going to be the one that is normal to the plane. Just like with the line, it's going to go straight to it at a 90-degree angle. The problem is, how do we know where that point is? Well, we don't, all right? We're not going to know. So what we're looking at is going to be something like what you see in this picture here. So let me scroll it up. So we have point P, which is not in the plane, and we have points down here which are in the plane, Q and R. Now R is that optimal place where it's hitting at a 90-degree angle. So the distance between P, the point, and the plane is the magnitude of the vector from R to P or P to R. So it would be the magnitude of this connecting vector at a 90-degree angle. But I don't know how to find point R, right? I don't know how to find it. But if I have the equation of the plane, then I have some point that's in the plane. So just some arbitrary point Q. And I have a normal vector to the plane. That's how I describe a plane, is with the scalar equation of the plane. So I have a normal vector and just some arbitrary point in the plane. If I connect that arbitrary point to the point P, it's probably, almost certainly not the optimal point. So it's coming off at an angle. But if I shine a flashlight this direction, notice that the projection of the vector QP over here onto this connecting vector, that's the distance I'm looking for, right? So when I'm looking at this, the projection of QP onto this is what I want. But this perpendicular line connecting R and P is parallel to the normal vector. So this distance over here in red is the same as this distance over here, the top of this rectangular box, down to point Q. So I can project QP onto the normal vector, and that would give me the perpendicular distance between the point and the plane. Now, the magnitude of that projection is also called the component of QP onto the normal vector, and we can compute that by taking the dot product of QP with the normal vector and finding its absolute value, because dot products are scalars, and then dividing by the magnitude of the normal vector. So this will give us what we need. This is the formula for finding the distance between a point and the plane. Let's work through example 9. We have a point not on the plane, and we're given the equation of a plane. Now, in this case, we're given the equation of the plane in general form, and the 3 is on the wrong side. If we moved it over so it was equal to 0, it would be -3. So that d, which is the combination of all the different constants, is -3. Now, when we're looking at this, I know the normal vector is going to be the coefficients of the variable terms, x, y, and z, so 4, 2, -1. I need a point in the plane. How do I get a point in the plane? Well, all you have to do is pick 2 variables and find the third one. Now, the easiest thing to do would be to say x is 0, y is 0, so z is -3. So that's the point 0, 0, -3. But just for fun and to make it harder, since I always want to do the hardest ones I can sort of in the lecture so that you have easier things to do in the homework, we're going to choose something different. But 0, 0, -3 would be the easiest point that is on the plane. It satisfies the equation. So what I did instead was I chose x is 1 and y is 1, and I plugged them in up here, or 2. Yeah, y is 2. X is 1, so I got 4. Y is 2, so I got another 4. So -z is equal to -5, so z equals 5. So that gives me the ordered triple 1, 2, 5. So that gives me another point that's definitely on the plane. It's our point Q. We certainly don't know that it's on the normal vector. I mean, it's almost certainly not the one that we want, point R. So what we're going to do is we're going to find the vector QP, which is going to give us this vector, 4, -3, -5. And then to find the distance between the point P and the plane in which Q lies with normal vector n, we take the dot product of QP with n, so take the dot product here, and you're going to take the absolute value of it, which is going to give us 15. And we're going to divide by the magnitude of the normal vector. And the normal vector came from the coefficients of x, y, and z. And so that was 4, 2, -1. So when we square those, add them together, and take the square root, we get 15 divided by the square root of 21. And we can take a look at this one as well in CalcPlot 3D so you can see what it looks like. So you can see right here that I have point P out in space, and I have point Q, and then I've got a normal vector, and I drew the normal vector coming off of point Q. All right, so, but what we're measuring is the distance from the pink ball straight to the plane at a 90-degree angle. All right, so it's from here to here. Okay, and that distance turned out to be 15 divided by the square root of 21. Now, how can planes intersect? We talked earlier about how lines in three-dimensional space intersect. So let's talk about how planes in three-dimensional space can intersect. When we're talking about planes in three-dimensional space, there are lots of possibilities. So I have pictures. They're not the greatest, but I couldn't find better resolution. One possibility is 2 of the planes are parallel, and the third one cuts through both of the parallel planes. But in this case, there's no single point that's on all 3 planes, right? 2 are parallel and not the same, and the third plane cuts through them both. It is possible, and this would be our 3D coordinate system, that 3 planes intersect at a single point, and that single point where they intersect, of course, is the origin. So that would be the YZ plane, the XZ plane, and the XY plane. They intersect at one point and one point only, and that would be right here at the center. That's the origin. So that's a possibility. And then we have more possibilities down here. We could have that all three planes are distinct and different. None of them are parallel. They each intersect the other, but not all at the same time. So again, they intersect at lines, but not at the same time. So there's no point in common. But it's a fundamentally different situation from when two are parallel and you have another one crossing. So a different situation, a different geometry. You could have that all three planes are parallel, so there's no point in common, which again, there's no point in common, which is like this one and the one above, but still very, very different geometry. You could have them all connecting at a line, and this is like a pinwheel or a water wheel where they're connecting at a line. So in a water wheel, you have the spokes coming out, but the rod in the center touches all of them. All right, so you do have the intersection of three planes, not at a single point, like in the coordinate axes, but instead at a line. Now, we also have the possibility of the intersection being a line if two of the planes are the same plane and they intersect the other plane. But if the two of the planes are the same and one is parallel, then there's no point in common. And then, of course, they could all be the same plane, in which case they intersected all the points in the plane. So how are we going to distinguish? When we're talking about lines, we looked at first, are the lines parallel? If yes, are they the same line or are they parallel lines so they don't touch at all? All right. If they're not parallel, then the question was, do they touch once or are they skewed so that they don't intersect ever? With planes, there are more possibilities, but we start sort of asking the same kind of question. Are they parallel? If they're parallel, then their normal vectors would be multiples of each other. So if they're parallel, their normal vectors are scalar multiples. They're also parallel. If the two planes intersect, do they intersect at a line or are they the same plane if they coincide? And or is it a single point? So it could be a line, a single point, or the entire plane if they're all three the same. So they might intersect, they might not, they might be parallel, they might not. If they intersect, it could be a line, a point, or the whole plane. So to find the line of intersection of two planes, let's say we have just two planes and they're not parallel. If they're not parallel, then they must cross at a line if we only take two planes. So two planes would be like two sheets of paper, and if they're not parallel, then they have to intersect at a line. So you can see the line right here where they intersect, where they touch, right? So when we're looking at that, how can we find the equation of that line? If the two planes are not parallel, the two planes must intersect at a line. So in example 10, we're going to start with two planes. So we have x plus y minus z equals 3 and 3x minus y plus 3z equals 5. Now, we don't have points on the planes, but we can get their normal vectors from the coefficients of x, y, and z. So 1, 1, -1, 3, -1, 3. The center one has a 1 for the first plane and -1 for the second. So you'd multiply by -1 to get from 1 to the second. But 1 times -1 does not give me 3. So they're definitely not parallel. Their normal vectors are not scalar multiples. Our planes must intersect at a line. So we're going to choose one of the variables, x, y, or z, to solve for in terms of the other variables. So we're looking for the equation of the line where they intersect. So typically we might choose z. Some textbooks prefer to choose x. We don't typically choose y. I don't know why, it's just convention, it's just our habit. The one we choose to solve for, or a convenient multiple of it, will serve as our parameter, right? So we're going to go ahead and start off by solving for z as the parameter. So I'm taking my first two equations of the plane, and I want to eliminate one of the other variables. So I want to solve for z. So that means I need to get rid of either x or y. And because of the equations of the plane, it's already easy to just add the two together, and that will get rid of y. So that gives me an equation in terms of just x and z, and I want z. All right, so the next thing I can do is I can solve for x in terms of z. So z is going to be my parameter t, if you will. So I'm going to solve for x in terms of z, which gives me this equation right here, right? Now, coming back to the original equation, I'm going to solve it for y. So I also have to represent y in terms of z, since z is going to be my parameter. I already have x in terms of z, which is this expression right here, the quantity 8 minus 2z divided by 4. So I solve one of the planes for the variable y, whichever one is easier. And then I replace the variable x with what it is in terms of z. And this will give me another expression, another equation for y in terms of z. And then I have three different parametric equations. So I have x in terms of z, y in terms of z, and z is itself, right? And I replace the z with a parameter t. Now, if we're going to plot this, again, we're going to plot this in CalcPlot 3D as a space curve, all right? So you can see right here that I've plotted the equations as space curves. So again, click on select, come down to space curve, and it will open up this three-part parametric equation, x, y, and z in terms of the parameter. So what I've done is I've gone ahead and plotted that particular one. So I've plotted them. Now to find the symmetric equations, we just solve for the parameter t, which will give us the equations that you see down here, all right? So we've got these in terms of x, y, and z with +1 coefficients. It gives us pretty nasty denominators. Notice that our denominators are fractions themselves, and that's the only way that we could do it. Now, this gets back to maybe we don't choose z to be our parameter. Maybe it would be better to choose a multiple of z to be the parameter, or a different one. So in this case, what if we had chosen our parameter to be half of z instead of just z? So z equal to 2t. Would that have simplified our equations any? So coming back to the expression for x, where I had 8 minus 2z all divided by 4, I can replace z with 2t instead, which will give me 8 minus 4t divided by 4, which is 2 minus t. And in this parametric form, there are no fractions. So when I convert it to symmetric, it will be far simpler. Solving for y, I had it in terms of z, 1 plus 3 times z divided by 2. If I let my parametric relationship be that z is 2t, then I can get this fraction to cancel out, and I get 1 plus 3t. And then instead of z being t, z will be 2t. But notice that these parametric equations are far simpler. And then when I solve for t to put them in symmetric form, I get much nicer symmetric form right here. So you can see the advantage of choosing what we call a convenient multiple. What if we had chosen x as the parameter instead, or even y? We would come up with different equations for the same line. So again, going back, let's say that we want to make x our parameter instead of z. So we eliminate y just to get x or z in terms of x, since x is going to be the parameter. Coming back to this equation, we would get z equals 4 minus 2x, and x is our parameter, so 4 minus 2t. Then we take one of the equations of the line, and we replace the variable x, or rather z, with its expression in terms of x, and we get something for y in terms of x, 7 minus 3x, or if x is t, 7 minus 3t. And then we have x is t, 7 minus 3t, and 4 minus 2t. And then we would graph that. So what are we seeing when we look at this plot out here on CalcPlot 3D? What are we seeing here? We see the two planes. One of them is sort of this purplish blue on this side, and the other one is red. And those symmetric equations and parametric equations are giving us this yellow line right here that is between the two. So if you turn it on each side, you can see the line from both directions. And that means that that is the line that connects the two planes. Now we have two final things to talk about in the relationship of planes to one another. This one is finding the angle between two intersecting planes. So we have two planes. They're not the same plane. They're not parallel, so they intersect at a line. And we want to know what the angle between them is. So if we're looking at a picture like this is sort of like, well, you can imagine like a binder maybe, and the two covers form the planes, and you want to know this angle that's between the planes. Well, it turns out that the acute angle between their normal vectors is the same angle as the angle between the planes. This is just a geometric relationship. So the angle that we have here, theta, the acute angle, right, between 0 and 90 degrees, is the angle between the two normal vectors. So in order to find it, we simply need to find the acute angle between the two normal vectors. And to do that, we can use the dot product. So the dot product, again, is the magnitude of one times the magnitude of other times the cosine of the angle between. So we can solve for the cosine of the angle or solve for the angle with the arc cosine of the absolute value of the dot product divided by the magnitude of the two. We want the angle to be between 0 and pi over 2, so we want it to come out to be positive. So magnitudes are always non-negative, and in order to force it to be positive, we simply take the absolute value of the dot product, and this will give us that angle. So in example 11, we want to measure the angle between two planes. Now, how do we know, first off, that the planes aren't parallel, either the same plane or parallel to each other? Their normal vectors are 1, 1, -1, 3, -1, 3, coming from the coefficients of x, y, and z. Again, to get from 1 to -1, you'd have to multiply by -1. But 1 times -1 doesn't give you 3 in the first component. So they're definitely not parallel. So they have to intersect at a line. We're going to find the dot product between the two normal vectors. So remember, you just multiply corresponding components together. And then we'll take the absolute value of that. I got -1, so I'll take the absolute value, which is 1. And because the dot product didn't come out to be 0, then I know that the angle between them isn't 90 degrees. They're not perpendicular. If it came out to be 0, they would have to be 90 degrees apart since the cosine of pi over 2 is 0. And then I find the magnitude of each normal vector, and I take the absolute value of the dot product, divide by the product of the magnitudes of the normal vectors, and I get a decimal representation. Then I find the arc cosine of that, and it comes out to be about 82.39 degrees. Right? Now, one last thing, find the distance between two parallel planes. Now we found the distance between a point and a plane, but now we want to find the distance between two planes that are not the same plane. How do we do that? Well, it's essentially the same thing as finding the distance between a point and the plane, because this P is inside of another plane, but I can find a point on that plane and then find the distance between them. So in this case, we pretty much already know how to do it. It's the same process. So the distance D is going to be the absolute value of the dot product between Q and P divided by the magnitude of the normal vector of one of the planes. So again, this is the projection of this QP vector onto the normal vector, which gives us that perpendicular distance there. And we have one last example that we can go through. Now this one, when you prove it, it gets a little bit more complicated. So Q would be a point in the first plane. We'll say it's x1, y1, z1. And P is going to be a point in the second plane. We want the distance between the two planes. All right, so P might be x naught, y naught, z naught. And n is the normal vector of the plane that contains Q. All right, so it's an ABC. And the equation of the plane which contains Q then would be given by AX plus BY plus CZ plus that D thing, or K, which in this case is the opposite of D. All right, so do we really need to know the coordinates of Q? And the answer is we actually don't. There's a way of working out this formula where we don't need to know it. Since we know that Q is in the plane, we know that if we plug in the coordinates of it, x1, y1, z1, we must get a true statement. So this basically means that K has to be negative ax1 minus by1 minus cz1. So by the definition of the vector from Q to P, which is x1 minus x naught, y1 minus y naught, z1 minus z naught, we know that the dot product of Q to P with the normal vector of the plane containing Q is going to be given by this equation right here. So again, dot product multiply corresponding components together. So we have this equation right here. Once we have that, we can go ahead and multiply these out. Since they're all scalars at this point, we can use the distributive property, and then we can rearrange terms a little bit, and we can replace what we found to be K, or negative K, with this ax1 plus by1 plus cz1, which is the opposite of that constant. And then we end up with this expression right here, which has to be the dot product of QP dot the normal vector. So we don't actually need to know the points of Q, we just need this K. So we need K, but we don't actually need Q. So in other words, this formula that we have right here, which you can use, there's nothing wrong with it, can also be written in this form right here, where we have ax naught plus by naught plus cz naught plus k, all divided by the magnitude of the normal vector. Now let's go back up and remind ourselves, what was k again? All right, so here's the equation right here that we're looking at. And k is simply the constant that's added to the variable terms on the left side of the equation. So I don't need the coordinates of Q, I just need to know what that constant is, which should be pretty easy to pick off if I have it in general form. So for example, let's take a look at this equation right here. Now this is not in general form yet because the 5 is on the wrong side. So if I subtract the 5 over, then k is negative 5. So I don't need to find a point Q to get k. I can still find the formula using this. Now, if it's in the standard form, which we can read the point Q directly off, then I might as well use this form of the formula instead. But if it's in general form, then I would probably use this form. Again, x naught, y naught, z naught is the point on the other plane. K is on the point on the first plane where Q was, and ABC is the normal vector from the plane where Q was. So let's find an example to work. So we have example 12. We want to find the distance between two parallel planes, right? Now, obviously, if the planes aren't parallel, then the distance between them is changing. So it wouldn't make sense to do that. So we're talking about the distance between two parallel planes. Now, how do we know they're parallel? Well, the coefficients of the x, y, and z give us the normal vector, which is 5, negative 2, 1, and it's 5, negative 2, 1 on that one. But they're not the same plane because their constants are different, all right? So in the first one, k would be negative 6, and in the second plane, k would be positive 3. Again, remember, you have to move it over to the left so it's equal to 0. So we know they're parallel because, well, their normal vectors are equal, all right? But as long as they're constant multiples, they would be parallel. Their constants are different, so they're not the same plane. So in this case, We can do various methods. So I need a point on one of the planes. So I chose x equals 1, y equals 1 in the first one. And then I got the point 1, 1, 3. I could also have chosen x and y to be 0, and then z would be 6, and I would get 0, 0, 6, which would have been far easier. So again, I'm doing it the hardest possible way, but you can always just choose wisely, right? And now what we want to do is we want to take the normal vector and the value of k from the other plane that we haven't used yet. So we chose our point P. So this is our point P right here. And now we need to choose k and our normal vector from the other plane. So k in this case is 3. Our normal vector will, I mean, they're parallel and exactly the same. So it's 5, negative 2, 1. And we simply plug it into this formula down here. So our x naught, y naught, z naught is our 1, 1, 3. K is 3, and the normal vector is 5, negative 2, 1. And we find its magnitude here. And when we work out all of the arithmetic and algebra, you get that the distance between those two parallel planes is 9 divided by the square root of 30. Let's go ahead and take a look at what that looks like. All right, so we can see that we have two parallel planes. Now, keep in mind that the reason why they're not showing up as exactly parallel is because CalcPlot 3D graphs the images in such a way that they always look three-dimensional, all right? So they're looking three-dimensional, but they are in fact parallel, all right? So you've got these two parallel planes and we're finding the distance between the two, right? So I hope that you have gotten a lot out of this particular video. What we're going to be doing in the next video is we're going to be talking about something called cylinders and something called quadric surfaces. So quadric surfaces may include some types of cylinders, but not all cylinders. And cylinders in the mathematics sense, at least in multivariable calculus, does not necessarily mean the shape of a Coke can, which is a right circular cylinder. We're going to see that cylinder actually carries a different meaning in multivariable calculus. So I hope you'll join me for the next video where we talk about cylinders and quadric surfaces.